So we are going to start dealing with, now that we know pretty much every antiderivative technique we need to know for this class, we're going to start solving tougher differential equations. And we've already solved some differential equations back in Unit 7. Differential equation is when we just have some derivative equal to something, and we usually have an initial condition. And if I ask you to solve this, I'm not going to give you anything else. I just say solve this, and your solution would be the function, the antiderivative that satisfies these conditions. Okay? So for this differential equation, we would have a general solution and a particular solution. The general solution includes the plus c. So with the plus c. So I would just take the antiderivative. I'd get x squared plus 3x plus c. And this would be the general solution to this differential equation. The particular solution, kind of the ultimate goal, is to find what c is where we use this initial condition. So I'd get 5 is equal to 0 squared plus 0 plus c. C is equal to 5, giving me my particular solution, y equals x squared plus 3x plus 5. Okay? And this is something that we've already been able to do. You've done it in Unit 7. So this is not new to you. But there will be some new differential equations that we're going to deal with today. This is somewhat new, this one right here. And it's new because it's a differential equation where you need u substitution. So let's go ahead and solve this, where dy dx is equal to x e to the x squared if y of 0 is equal to 2. So again, we want to find the antiderivative, but then we want to find that c using this initial condition. So I set u equal to x squared, because it's the power of x, and its derivative is a version of x here. Du will equal 2x dx. Dx will be 1 over 2x du. Okay, I am taking the antiderivative of this, so I can just kind of write that in there. So it would be the antiderivative of x e to the u, and then I replace dx with 1 over 2x du. We should have done this enough that that is not new to us. We see that the x's will eliminate. I will be able to take the antiderivative of this. It would just be 1/2 e to the u plus a c. We need that c. And now we have this equation y equals. Instead of just an expression of the antiderivative, we need an equation. I'll show you where that equation comes from in a little bit. Why we just don't, not necessarily just plopping down a y. Okay, so I'm going to go ahead and replace the u with x squared. And here is my general solution with the plus c. Well, using the general solution and my initial condition, we can find c, right? The last step to these differential equations that kind of differentiate them from just straight antiderivatives. So I would say 2 is equal to 1/2 e to the 0, e to the 0 plus c. E to the 0 is 1, don't forget that. So this would be 2 equals 1/2 plus c. That's 4/2 minus 1/2. C is equal to 3/2. And now we have our particular solution. Y equals 1/2 e to the x squared plus 3/2. Okay, so I just took this general solution. I found c, and then I rewrote the general solution with c being 3/2. C plus 1/2 equals 2. Okay. Great. So a little bit tougher because it's U substitution, but this is really not that much tougher than Unit 7 ones, just with a different antiderivative technique. Okay. Well, now let's deal with some other different looking differential equations, like this guy right here. dy dx is equal to negative x over y. Why is this tougher? Well, because it has multiple variables. It doesn't just have x's. It has x's and y's. Okay, it's like, man, I have to take the antiderivative of negative x over y. I'm not sure how to do that. And really quickly, it's not negative 1/2 x squared over 1/2 y squared. We know that this is not going to be correct. No. Okay. Now, before we get into finding the solution, let's remember when we had derivatives that looked like this. Let's recall Unit 5, which was implicit differentiation. This is an implicit equation. Equations like this, where we had x's and y is not easily solved for, ended up looking like, you know, shapes that we see in the world, like circles, like ovals. We ended up looking at a graph that looked like the thing in the back of your throat. You know, we did all of those and we found derivatives of them, and we found like horizontal tangents and vertical tangents and stuff like that. Okay, and the key with these is that they're not functions. For a given x, there are multiple ways potentially. Okay, but we asked you guys to be able to take the derivative of this so that you can find dy dx, so that you can tell me what slopes of tangents were at specific points on the implicit equation. Go ahead and take that derivative. Let's see if you remember. It's a nice little review question right here. Do you remember that? One thing that we need. No, but I like the attempt. Check with your neighbors, see if they remember. Nice. You need a 12y squared. Yep. Okay, let's recall that when we take the derivative of these variables, it's essentially using the chain rule every time. We took the derivative of the outside, leave the inside alone, and then we kind of take the derivative of the inside, and it's essentially multiplication. It would be the change in x over the change in x, which is 1, which is why we don't include dx dx, while we'll just write it as 6x. But when I do it with 4y cubed, the derivative of the outside would be 12 stuff squared. But then when I multiply that by the derivative of y with respect to x, I write dy dx after it. So it would be 12y squared dy dx. And then the derivative of this constant is 0. We should know that. And then we can solve for dy dx by subtracting 6x and dividing by 12y squared, giving me negative x over 2y squared, right? This is, you know, review, but I can see how we struggled on that because it's been a while. Well, today and the next class and the following class a little bit, we will start here and go this way and end up there. Okay, we're going to backwards implicitly differentiate. We're going to implicitly integrate. Fantastic. How are we going to do that? How do we start here and go backwards? Well, the process is called separation of variables. Okay? Separation of variables. To backwardsly I'm not going to say backwardsly, to implicitly integrate instead of differentiate. Okay, now step one will be to separate your variables. It's super duper important. Whenever we see x's and y's, separate your variables. What does it mean to separate your variables? Put your x's and dx's together, put your y's and dy's together. And don't just move them magically, move them algebraically by multiplying or by dividing. Okay? So with this situation, it's essentially cross-multiplying. Multiply by y, multiply by dx, but exactly what we are doing is multiplying both sides by y, so that y is with dy, and we are also multiplying both sides by dx. We could do this one step at a time, but I'm just doing them both at the same time. So when I multiply by dx, the dx goes away. I'm just left with y dy on this left side. And here the y's will cancel, leaving me with negative x dx on the right side. Right? Well, now that I have my y's with my dy, my x's with my dx, I am ready to to integrate both sides, anti-derive both sides. Okay, and I don't have to worry about anything crazy because I have the antiderivative of y with respect to y. I have the antiderivative of negative x with respect to x, and I can do that. Okay, now what do I get? Let's see. I'll have 1/2 y squared plus a c, right? Because I'm taking the antiderivative, I need a c. On the right side, I'll have negative 1/2 x squared plus a c. Okay? We have a general solution right now. We have an equation that's derivative is negative x over y. Okay, but we can do a little bit more. We can simplify it. We can make it a little nicer. So what's one thing we can do we think, that can make this look a little nicer? Right. Now, what do we think we get when we have c and we subtract the c? Do the c's cancel? No. This is good. I'm glad that we are realizing this. I'm not having to tell you. This is a c. This is a potentially different c. You don't know that they're the same. So what happens is if I subtract c1 from both sides, what I create is just a new c, not 0. We could call it c3 or just c. Okay? It's going to be really important, and it's going to help us if we just have one c on one side rather than two c's on both sides. Well, I don't know what c is. C could be positive or negative, right? We will always put it plus c rather than minus c because it's the same. But I don't know, we just like to use pluses more than minuses. Okay, so this is good. This is a general solution. However, what we will find is that even though when we started with equations like this, we took the derivative of that, when we go backwards, the test makers are going to ask you to put your answers in the form of y equals. Okay, so you have to read, oh, they want my solution in the form of y equals, so I need to solve for y. For some of these, it'll be easy to do. For some of these, it'll be very tough to do. Okay, so I'll multiply both sides by 2. Well, now I have a situation. If I multiply this side by 2, what happens to C? Good. So C times 2, I could write as 2C, but what's 2 times a C? It's just another C. So I will write this as just C, even though I multiplied it by 2. This is just a constant. If I wanted to, I could have said, oh, this is, version 3 of my C. This would be version 4 of my C. You do not have to do that, though. You can just write it as C. Okay? And then finally, to solve for y, I need to square root both sides. Now, that would be square rooting the entire side, which means the C would end up underneath your square root. Excellent, Mr. Lentz. And since we're square rooting something squared, the original value could have been a positive or a negative. We need a plus or minus there for this specific situation. Okay. Boom, we have just backwards implicitly differentiate. We've just implicitly anti-differentiated. Let's do another one. Step 1, separate your variables. Step 2, anti-derive both sides. Then, essentially, just solve for y algebraically. In this situation, I need to take the cubed root of both sides, or just take both sides to the 1/3 power. Do I need a plus or minus before this cubed root? No, an odd power retains its sign, so it's only when we have an even power, an even fraction, that we need the plus or minus, okay? If it's a fractional power where it's, an odd denominator, something like this, it's going to retain its sign. Now, if we talk about something like this will always be positive. Why? Because we're going to square something eventually. Okay, this could be positive or negative. and it'll remain positive or negative.
So if the x squared inside the
Yes. Yep. If this was just squared. Yeah. Okay. Good. Now, what's the one thing that we haven't been doing? Yes, we haven't been solving for C. Okay. Now, we need to be very, very careful because our questions are going to change up a little bit when we're asked to solve for C. So now I have another kind of, implicit derivative that I want to anti-derive, but I have a initial condition. So now let's go ahead and solve this, but find C. Because I'm told what this function is at a point. And we should be questioning something once we get there. We should get y equals plus or minus root 5x squared plus c for our general solution. Now we use our initial condition. And I say 2 is equal to plus or minus root 5 times 1 squared plus c. Does this mean there are two c's? Well, I square both sides, and if I square both sides to get rid of the square root, the whole plus or minus ends up just being a plus. So I just get this, which means c is just -1. So plugging that c in, I get y equals plus or minus root 5x squared minus 1. Everybody with me? Nothing too complicated, right? Well, technically that is wrong. Mr. Owens, you got an earbud in your ear?
No.
All right, good. Just checking. Thank you. Haven't been over there in a while. Okay, technically that's wrong. Okay, and it's the way the question was asked that makes this wrong. Okay, who can tell me why this is technically wrong? Yes, good, Mr. Van Buren and Mr. Urban. Because they're asking for a function. In terms of a function, okay? Now, what does this mean? Well, this means that, the solution, the general solution could look like, an oval, right? An oval is not a function. They just want a function. Well, turns out if I just gave them half of the oval would still satisfy this differential equation, and it would be a function. But if I have a top half and a bottom half, then all of a sudden, that's not the correct answer. And the half that they want you to find is given by the initial condition. We are told y of 1 is just equal to 2. Even though in reality, most likely, it's equal to plus or minus 2. But they're saying, no, I just want y of 1 to be equal to positive 2, which means for this solution, they just want the positive half of my oval, or my circle. In this case, it's an oval. So this is technically not right because I don't want two y's for a given x. Instead, I just want the positive half. Because they asked us for a function, and they told us that when x is 1, y is only 2. This is our particular solution. Mr. Lenz.
So if they were to say something like y equals -2, would you give them a negative square root?
Exactly. If we were told that y of 1 is equal to -2, then we just need a negative, because it'd be 5 times 1 squared minus 1, which would be root of 4, which is 2, but we need the negative side. Okay? So let's kind of do that on your own. It's really the same type of question. Let's change this 5 to a 4. And let's go ahead and solve this differential equation in terms of y equals f of x. So f of x. Not a positive half and a negative half, just one of the halves. Okay? Any questions about that? All right, good. So we know at least what the equation is for some of these differential equations. There's going to be another approach that we are going to take, a more visual approach to kind of not only kind of understand what the equation is going to be, but understand what it looks like, because we kind of don't know what this looks like. Ends up being like an oval. Okay? So we're going to help understand our solutions visually. We are going to use things called slope fields to do that. Okay? Slope fields is a visual representation of the differential equation that will help us understand what potential solutions look like. I'm going to type that. visual representation of the differential equation that will help us see potential solutions to the differential equation. Okay? And we are going to create a slope field for that first differential equation that we looked at, negative x over y. Okay? Now, what is a slope field? Okay, besides that definition. Okay? It's just a bunch of slopes. A bunch of tiny tangent slopes that we are going to graph at random locations. How are we going to graph tiny slopes? We are going to plug in random points into your dy dx. Stay with me, Ms. Quadri. And then we are going to graph their tiny slopes. Yep. Literally. For example, the point 1, 1. If I plug in 1, 1 into dy dx, and I just pick this point randomly, I'll get negative 1 over 1, which is negative 1. At the point 1, 1, my equation must have a tangent slope that is negative 1. Now, what does this do? This actually helps me know what a solution could look like, okay? Because I could have some graph that goes everywhere, but if I get close to 1, 1, I'm going to have a tangent slope that's negative 1. So all of a sudden I know, at least in this area, my solution has to look like that. Okay, well that's valuable, but not very valuable, right? Because I can do anything else around there. Well, let's kind of expand where we look at. Let's look at like 1, 2. Well, dy dx is going to be equal to negative 1 over 2. Negative 1/2. Well, at 1, 2, I need negative 1/2. So a little bit shallower. Let's look at 0, 1. I'd have dy dx, which is equal to negative 0 over 1, which is 0. What is a 0 slope? It's horizontal. At negative 1, 1, I'd end up with a slope of 1. At 1, 0, it would be negative 1 over 0. What does 1 over 0 look like for a slope? It looks like something, actually. It's vertical. It's very important. If you have a dy dx that is a 0 in the denominator, that means we're moving up and down, but not left and right at all. That'd be like that over there. And negative 1, negative 1, I would see the slope is negative. 0, negative 1, the slope is 0. 1, negative 1, the slope is positive 1. And we could continue to do that. Okay? And I could find that this slope is positive 1/2. This slope would end up being negative 1. This is negative 1. And this one? Nope. I was a little off. Zero. 1/2. Okay, and we can continue to go until we see that. Okay, that's the slope field for negative x over y at a lot of different points. Now, that means my graph, whose derivatives are negative x over y, has to follow these tangent slopes. So if I start at a point and say, okay, my equation has to pass through that point, we can follow the tangent slopes as best as you can, because your solution must have all of these tangent slopes, and all of a sudden we can see what my solution could look like. What will it look like? What will it look like? It's a circle. Now, is this circle the only possible solution that satisfies this slope field? No, right? Because I could have a circle right here. I can have a circle out here. Ugh. You know what I mean. Where does that whole fact that I can have multiple, in fact, infinite amount of solutions show up when I'm solving a differential equation? We've already solved this differential equation, negative x over y. Where does the fact that I can have multiple circles show up? The what? No? Yes, C. I heard C can't change. I'm like, no, it's not. No, the C is a constant. It can be anything. Let's go back to our solution to this. Look at this guy. So that's exactly what you meant? All right, sorry, Mr. Buckingham. So this was my solution. It's got a C. Now, if I could do a little bit of work and then create it like this, and actually instead of solving it for Y, let's solve it for C. What do I see? The equation for a general form of a circle with a radius C. Right? You didn't know that because we didn't solve for C, but there you go. Any circle will satisfy this differential equation. Well, this slope field confirms that any circle will satisfy this differential equation. Cool? All right. Now, are you going to be expected to create a slope field that's large? No. But you will be expected to create a slope field where you are given a specific set amount of points, like this point, this point, this point, this point, this point, this point, that point, that point, that point. And you're going to do that for your homework, okay? I'm going to give you AP for your response packet. And you'll see some of those types of problems. Other questions that you will see will deal with graphing potential solutions. So you'll be given the slope field and you'll have to kind of draw the solution, like this. Mr. Lent's question.
For real world application, I guess this would have to do with like gravity wells and magnetic field.
Sure, for sure, definitely. Right, because it's like, where does it go? Definitely, okay? For this class, it's more of, I can't solve this differential equation. I don't know how to take the antiderivative, but I can visually see the solution. This is an example of some differential equation, most likely, that I couldn't solve. But here are what the slopes look like. Now, can you sketch the solution like that? Go ahead, Reed, do it. Yeah, go ahead. Follow the slopes. Oh, you're passing, you skip. You got to go through this dot right here. Yeah, so start at the dot. It was a trick, sorry. Good, good. Yeah, sure. And then go to the left of the dot. Yeah, right? So you got to just make sure your tangent slopes match up with your graph, and you'll be expected to know how to do that. Give them a round of applause. What else do you have to do? Well, you will be given a slope field, and you will be asked, hey, which differential equation creates this slope field? Okay? Now, what do I do for these problems? I look at specific ones that I know. If I look at here, when x is 0, I notice that I have vertical dy dx's, like 1 over 0, some number over 0. I notice that when x is positive, dy dx is positive but decreasing. I notice when x is negative, dy dx is negative, but decreasing. Go ahead and discuss with your neighbor which differential equation out of those four creates that slope field. All right, Mr. Head, which one do you get?
It's 1 over x.
1 over x is correct. Now, you guys know how to solve this differential equation. What is the solution to this differential equation? What is the y equals that solves this? Aha! Natural log absolute x plus c. What does that look like? I showed you the other class. It looks like this on the right side, but then another that guy on the left side. So boom, you could see the solution, y equals log absolute x plus c, given the slope field. Okay, let's do another one just like that. Here is a slope field. Tell me which differential equation creates that slope field. What are some things I look at? I look at, oh, I have a line of 0 tangent slopes, and I have a line of tangent slopes that are 1. So 0, 0, slope is 0. It looks like 1, 1, the slope is 0. It looks like 1, 0, the slope is 1, but 2, 1, the slope is also 1. Okay, discuss what you think it is with a neighbor. What do you get, Miss Edmondson? Did you figure it out? X minus y is correct. Okay, good. Those are the easy ones, in my opinion. I mean, they're not actually, some of those could be the harder ones. But another type of question, before we leave, because we still have 3 minutes. Come on, guys. What do you think this is? Some other class in this high school that ends early? No. Here's a slope field. Which of the following could be a solution, a specific solution for this differential equation? We have all these possible y equals. You're not matching the slope field with the differential equation. Instead, you are looking at the differential equation slope field, and then you are matching its possible solution. It looks like something like this satisfies that. What's that, Mr. Klobusnik? The x cubed one. You guys, in the future, this whole, all right, Mr. Messner, we have 3 minutes left. Can we start backing up? That's not flying, okay? We go until we're done, please, or I will hold you after the bell. No, I probably won't do that, but stop doing it, all right? There's stuff to learn, and I want to teach you, okay?